Hello, my name is Desmond Parker with A Plus College Ready. Today we will be talking about molecules. Molecules basically are atoms that have bonded together to form new substances. Those new molecules have different properties than the original atoms do. So let's take an example of sodium chloride. Sodium, I should say, is a metal which when put in water will explode. Chlorine is a gas, which when you breathe it in, you cease to live. Well, when we take these two and we marry them together, we form a substance that is not like the original substance. It's actually edible. We can eat it, it doesn't blow up, and it doesn't kill us unless, of course, you take too much of it and it raises your blood pressure too high. But other than that, these substances have new properties. So we have two primary classes of compounds that we're going to focus on today. The first are molecular covalent compounds. That term can be interchangeable with each other. Sometimes you'll hear molecular, sometimes you'll hear covalent, but they are both the same thing. So our covalent compounds consist of only nonmetal atoms, and it actually is a vast majority of the type of materials or the type of substances that exist in our universe. Mostly covalent compounds. That's your proteins, your DNA, your clothing that you wear. Those are made out of polymers, which again are covalently bonded together. So when these atoms are bonded together, they share what we call our valence electrons. And that bond that they form, we call a covalent bond. So we have three types of covalent bonds that exist. The first is a single covalent bond, a double covalent bond, and a triple covalent bond. The bond strength typically increases as we go from a single to a triple bond due to the number of electrons being shared. Single bonds only share 2, double bonds share 4, triple bonds will share 6 electrons. And because we have so many electrons clustered in one place, you would really think that the bond length would increase, but it actually shrinks. So our single bond is going to have a longer bond length than our double and our triple bond. And that bond length increases as we increase the number of bonds. One thing to note that's very important is that when it comes to bond strength, is that a triple bond is not necessarily 3 times as strong as a single bond. So it depends on the type of bonding that occurs, which we will get into later on when we talk about hybridization and things like that. But just keep that in mind that bond strength will increase from single to triple. However, it is not, the order of magnitude does not increase by that same amount. So in general, when bonding occurs, is we're trying to follow what's called the octet rule. And the octet, think of oct, that's the prefix for 8. We generally want 8 electrons. Now, the one thing that's kind of deceiving about this octet rule, in my opinion, is that it's broken more often than it's followed. There aren't very many atoms that really truly will follow the octet rule. But for general purposes of what you guys need to know is that a vast majority of these atoms will. So some of the exceptions, hydrogen. Hydrogen is one of those that does not need a whole lot of electrons because it only has a 1s orbital. And s's only hold 2 electrons. So hydrogen is satisfied with simply having 2. Helium really doesn't bond with anything because it's one of our noble gases, so we really don't have to worry about that one. Lithium and beryllium both, excuse the typo on beryllium, is another one of our elements that does not need to have a whole lot of electrons. And then pretty much any atom that has the ability to have a d orbital does not follow the octet rule either. Now our second class of compounds that we we'll learn about our ionic compounds. Ionic compounds consist of a metal cation in most cases. There's one exception, and a non-metal. And when these compounds bond together, they tend to form what we call a crystal lattice structure. So the formulas that we're actually looking at for ionic compounds are really a reduced number, which will tell us the minimum amount of each atom type that we need. So sodium chloride in a crystal will have several mole numbers of sodiums and chlorines. However, if we reduce that down, we have one sodium, one chlorine. This crystal structure is highly structured, and it requires a lot of energy to break it. Outside of using water, ionic bonds are significantly stronger than covalent bonds. From a biological standpoint, however, the biologists tend to say that ionic bonds are weaker because they're operating in a solution environment. So in a solution environment, ionic bonds would not be considered strong. But for a chemist, we say ionic bonding is much stronger than covalent bonding is. Now, when we are bond breaking and bond forming, we have endothermic and exothermic processes, or endothermic and exothermic reactions. Exothermic is when heat is released into the environment. So think of exo, which is exit. So it is exiting our system and going out into the environment. And this is associated with bond formation. Please don't be confused here where it says condensing and freezing. Those are exothermic processes. Freezing and condensing are not chemical reactions because they are physical changes. However, that process is exothermic because heat has to leave the system in order for condensation to occur, in order for freezing to occur. So if we look at an energy diagram, and you guys need to begin to get familiar with this, because as you proceed forward through this course and through your AP course, you have to know these diagrams. So when I'm looking at exothermic energy, I will see that my energy of my initial reactants are at a higher energy than my products will be. That is because I had to release a significant amount of heat in order for this reaction to occur. So my products are at a lower, have a much lower potential energy than my reactants do. So on the other hand, we have endothermic processes. This is when I break bonds. So in order for me to break a bond, I need to absorb energy from my surroundings in order to do that. Again, melting and vaporization are a process, not a reaction. So in order to break those bonds, I must absorb energy. So looking at my energy diagram, and again, you need to know this one too, is that my products are at a higher potential energy than my reactants will be. So the delta H, or as we call it, the enthalpy, will be positive versus an exothermic where my delta H will be negative. So when it comes to bond length of our substance, we have an optimal distance that these atoms like to be at. So as you get further and further away from that optimal bond energy area where the potential energy is the lowest, your attractive forces begin to dissipate the further you get away. And as I get these two molecules closer and closer together, these repulsive forces exponentially increase. So ideally, there is a certain distance where these atoms are the most happy at, and that is the internuclear distance that we ideally want to be at. You will also see these in computational chemistry, where you will minimize the energy of a system. And when you get to this lowest energy, which is right here, that's when your system is considered to be energetically minimized, which will then make your simulations actually run. So let's take a look at a multiple choice problem from an old test. So our question is, the potential energy of a system of two atoms as a function of their internuclear distance is shown in the diagram. Which of the following is true regarding forces between the atoms when their nuclear distance is x? So go ahead and pause the video, take a moment, think about it, and let's come back and talk about it. Alright, so the first thing that we should really do is to do some process of elimination if we don't already know immediately what the answer is. And we want to eliminate those answer choices that we obviously know are wrong. So here at this point right here, this is when our net energy is the lowest. This is when our system is the most stable. So we need to find some place where it's actually talking about some type of stability. Now, if we look at, let's start at D. It cannot be determined whether the forces between the atoms are balanced, attractive, or repulsive because the diagram only shows the potential energy. Well, if we recall back to the last slide that we looked at, that these forces here are repulsive and these are attractive forces. So we actually can determine whether or not it's balanced, and we know whether or not they're attractive forces. So we can cross off D. For letter C, there's a net attractive force, so that is true, pulling the atoms together so the atoms will move closer. Now, the first part of this is true. However, the second part is not. The atoms will move closer. No, because we can actually see here when the atoms begin to move closer is that this energy shoots all the way up, which is not okay. So answer C is wrong. There's a net repulsive force. This is our clue right here. This is not a net repulsive force at this point. So we have to be left with answer choice A. Alright, I hope this video was helpful. If you have any questions, make sure that you direct them towards your instructor, and I'll see you next time.